How is everybody today? Good? Doing good? Hopefully. Hopefully. Yeah. Sorry that I couldn't quite get the video published yesterday's lecture yesterday. I have to re-render the thing in a video editor because the way that it's recorded by the camera is in like 12-minute chunks or 22-minute chunks. Sometimes there's it splits one video file up among many videos, and it has to do with like the hardware codec and all kinds of stuff like that. At any rate, I have to stitch them back together in order to publish them. And for some reason, whatever reason, while I was re-rendering the video, the re-rendering failed during post-processing, which is like the final step, so I had to re-render the whole thing, which takes about an hour, and it was, just not a great time. It is, all I have to do basically is set it up on YouTube and click publish, and that's all that needs to be done, so I'll be having that out, almost immediately after the end of this class. So we'll have yesterday's lecture up very shortly. And hopefully the same day, we will also have today's lecture, assuming that Kden Live doesn't goof up for miscellaneous reasons again. At any rate, hello. Well, so continuing on from our topic yesterday, we were talking about statements more generally, not just how to perform individual calculations using expressions, but how to run a series of those calculations together in order to actually form a program. We had talked at some length about if statements. We talked at some length about loops. And now we're going to view an example, another example of how one would construct an algorithm that does something useful. So, in the study of computer programs, there are certain classes of problems that are, shall we say, classic problems of the discipline. These are the types of problems that are very often presented in early undergraduate lesson material. One such algorithm is search algorithms. Other ones include sorting algorithms. We won't talk too heavily in depth about sorting algorithms. So essentially what a search algorithm does, it's very simple. It takes a data structure and returns a result based on whether some specified value exists in that data structure or not. Search algorithms have very, very wide-ranging applications. As anybody who lives in the modern era and has ever used Google will be able to tell you, highly optimized search engines are what have produced the modern internet, right? So searching is a non-trivial problem, and getting it right means that you become Google, or at least it did back in the 90s, late 90s, early 2000s. So, it's kind of interesting how, how many search engines have been relegated to the dustbin of history. Anybody remember Alta Vista? No? You guys too young for Alta Vista? Probably. Anybody remember Netscape Navigator? That was a fun one. No? Yeah. Those are very early. Alta Vista was an early search engine from the 90s, and Netscape Navigator was a very early browser from the 90s. But anyway, so searching algorithms are very important and make an interesting case study because the simplest type of search has a very simple implementation. We call the simplest type of search that you can perform linear search. And the reason we call it linear search is something that will be elucidated over the course of some slides. So, if we were to search through, let's say, a tuple to see if a particular value was in there or not, how would we go about doing that? Does anybody have any idea what the structure of this algorithm would be? Still pretty early in the morning? So the trick here is that you're not making any assumptions about the contents of the data structure itself, right? If we had some assumptions that we could make about the structure of the data, we would be able to come up with a more efficient algorithm than this. But in the absence of any kind of information about this data structure, any particular element of that data structure might be the one you're looking for, right? Therefore, it is necessary in the worst case scenario to check every single one of the elements in the data structure in sequence. So very simply, all that we have to do to implement linear search is to write an algorithm which traces through every element of the structure and compares it to the thing we're looking for, right? So, if we were to write that as an algorithm, let me just pull up a file, and we will get to work. Let's see, text editor. So, let me just comment out previous, oops, no. There we go. So, define lin search. Taking some data structure T, capital T, and searching for some element E. So, now, it's important, let me kill the lights a little more thoroughly. Is that a bit better? Better still? Is that so dark people are going to fall asleep? No? Okay. I'll just have to be more energetic. That'll keep people awake. So, we have a search operator in Python. This is the in operator. You remember from our list of operators that we can perform over tuples, we can do E in T, and that will return a Boolean which indicates whether or not the thing is in the thing, right? So, if we wanted to, we could return E in T, call this the end of the demonstration, and learn practically nothing. What we are about to do is the algorithm that operates inside of that in operation. So let's do it a little bit more interesting. And just to say, just for the sake of interest, let's return some more information than simply a Boolean yes or no. Let's return the index at which this element exists. So, essentially what we're doing is re-implementing the index method, which we also have available to us in the slides. It's actually a very good exercise to re-implement something that's been provided for you in a library, because if you can re-implement it, then you understand its structure. And if you understand its structure, you will be able to use it better than if you don't understand its structure. So, linear search. We want to iterate through every element of T in order to compare them to E. That's what we call, that's what that term, iterate, that's what it means to go over something with a loop, right? We iterate through a data structure when we construct a loop such that we examine each element of a data structure in sequence using a loop. That's what the term iterate means. Cool? Any questions so far? Okay. I know I asked that a lot, but it's an important question. So, we have an index I starting at 0. While I is less than the length of T, we do the thing. Don't forget to increment I by 1 Otherwise, the loop will be infinite loop. Thank you very much. So, under this construction, every time we use t at I, that will be the current value in the data structure that we are examining, right? We want to compare to see if t at I is the same as the element we're testing for. This is quite easily done. If t at I is equal to e, we do something, right? So in this case, we wanted to return the index at which this element can be found. So we return I. Now, if you wanted to do something a little more fancy, you could store the index in some kind of intermediate data structure and then return all of the indexes at which this element can be found. That's one way of going about it, but for the purposes of this algorithm, this should be sufficient. So, let's say numbers is equal to bunch of numbers, lots and lots of numbers. There we go. Print. Lin search numbers, and let's search for 7, just out of interest. Let's also return something that's not in the array, like 10. So, quick question for the class. What does this algorithm do if we do not, if the number that we're searching for does not exist inside of the structure we're searching for it in? What will be the result that's printed? Anybody got an idea? Yes?
Nothing.
Nothing. More specifically?
It's going to be like an empty bracket.
It's going to be an empty bracket? Well, in Python, the way that they handle this is they have a none type. So it's like a null value, but essentially what's going on here, if this while loop executes and this return statement is never hit, we pass through the execution of this while loop into blank space at the end of the algorithm. We're not actually returning anything here. So the way that Python handles functions that the way that Python handles it, if you reach the end of a function without having returned a value, is it returns a default value that's sort of baked into the language itself, called the none type. Basically, it's written none, like this line is implicit. So you see how none has been highlighted? It's because it's a keyword in Python. In the same way that true and false are keywords in Python, none is also a keyword. It designates a type that has no elements except none, which is like a null or doesn't matter or don't care value, right? However, we may want to return something more interesting here, so let's return, I didn't find it, the string. Now, in many programming languages, this wouldn't fly because this is a function which returns both an integer and a string differently depending on the context of how it operates. Most languages will disallow that sort of behavior, but because Python is very loose when it comes to its type system, this type of thing is permitted. I don't necessarily recommend it, but, you know, there I am griping about Python again. So, Python 3, topic 2.py. There we go. So, in the first case, the index at which we find 7 is 6. 0, 1, 2, 3, 4, 5, 6. That's correct. And 10 returns the string I didn't find it. Linear search. Any questions? Yes.
Let's say in the tuple or the list, there's the number we're looking for occurs more than once.
Yes.
So then how can we know both, like all the instances where it occurs?
You would have to modify the algorithm. So the algorithm as written exits out the first time it encounters something that matches E. If, however, we wished to modify the algorithm such that all valid indexes were returned, we can do that quite easily, and that might be a useful demonstration. Thank you for the question. So, let's say answer is an empty list. Rather than return this here and return that there, we say answer dot append. We'll get into append operations once we get into lists, which will be very shortly. Within this very class, in fact, we append I, and then at the end we return the answer. So, if we run this guy, you'll see that now our behavior has changed such that we now have a list of all valid indexes which are being returned. And in the case where no valid index is found, we return an empty list. The empty list functions somewhat like a null type, except you can add things into it if you want. At any rate, you can test to see if it's a null list just as easily as testing to see if it's a none type, to see if it returns something or not. Make sense? Good question, thank you. Good. So, linear search. Search through a sequence of values to find the first occurrence of the specified value. So another interesting thing about Python, because Python is Python and Python is relatively loose with its types, we can also modify this relatively easily. The same algorithm works on strings. So if I had a string, hello, how is the weather? And we wanted to print the linear search. How many times does the letter E occur? Or where does E occur? None? Interesting.
Don't you have to change it to string instead of numbers?
Oh, yeah, that'll do it. Ha! Thank you. Thank you. Thank you, thank you, thank you. See, I do not profess to be perfect. I appreciate it. So, obviously you have to use the correct input to get the correct output. Garbage in, garbage out. So, with this same algorithm, not modified one tiny little bit, the operation works just as well on strings as on tuples. This is another feature that's particular to Python. Most languages are more strict about their data types than that. But since a string has the same basic set of operations as a tuple, there's no operation that's being used there that isn't also defined for strings, so that's why it works. So, yes. So let's go through the manner in which this is implemented by the slides. So, most particularly, the way that I implement, let's do a side-by-side comparison here. Ooh. There we go. So the manner in which I implemented things, I had the loop on the outside and an inner if statement, which checked to see if the element we're looking at is the one we're looking for. In this case, that condition is baked right into the loop condition itself. And inside of the loop, we do nothing except increment the index. Then, after the loop is terminated, the status of the index is examined to see if, while we were in this loop, we reached the end of it. If we did not reach the end of it, we return the index. If we did reach the end of it, we return false, which in this case is equivalent to I didn't find it. Right? So this is another way of doing things, for sure. Whichever of the two of those makes more sense to you is fine, because they're essentially functionally equivalent, minus the fact that we're like returning multiple indexes in our version. So to contrast that, we can also have a version that returns immediately, which is very similar to the first version we did. And let's introduce a new coding construct. So it will sometimes happen that you wish to provide an instruction which breaks you out of a loop immediately at that instruction, not having to wait to reevaluate the loop condition. This can be especially true if your loops are large, right? The longer the loop is, the more time it will take for you to get back to the condition that you're evaluating, right? So we are provided with a break keyword. The break keyword exits the loop immediately upon that condition being hit. So if rather than returning immediately from the loop, you want to save the return statement for the end, which incidentally is better practice, although not sufficiently good practice for me to give you marks for doing it, but like sufficiently, like basically the reason that saving the return statements for the end is considered better practice is that then you have the input at the top and the output at the bottom. It means that you can more easily trace the line of execution through the program and not, be jumping all around with random return statements. But again, this is kind of like, this is a very secondary stylistic problem. Like most programmers, I would say, do not have any qualms about using return statements in the middle of functions. The slides think it's more important than I do. Let's just put it that way. Anyway, if you want to preserve that type of structure, what you can do is you can insert a break statement. As soon as this if statement evaluates true, it hits a break statement, closes this loop immediately without closing the function. We jump to the end of the while loop. And then we continue on with execution, performing the same check at the end to see if we had reached the end of the data structure and returning accordingly. Make sense? Any questions about that so far? This should be like, you guys, like, how are you guys doing with the material here? Is this like relatively, like, is this understandable? This type of stuff? You guys getting it? Let's see a thumbs up for if you're getting this. Okay. Yeah? Okay. Well, it's difficult for me to help without having a question, right? And it's interesting, right? Because like in the formulation of the question itself, you will often clarify the problem that you have, the conceptual problem, and prepare yourself for the solution to it, right? But so it takes intellectual work to develop the question, but that's always going to be worth it. Anyway, so so much for linear search. Okay. Now we're going to talk about probably one of the most useful parts of the Python programming language, which is relatively specific to Python, Other languages have similar constructs to these, but it's never presented quite so clearly and simply as in Python. This is like one of the very few advantages that Python actually has. It is the for loop. So while loops, you'll never completely dispense with them. But most of the time when you're writing a loop in a programming language, the reason that you're writing that loop is because you want to iterate over the elements of a data structure, right? Most of the work that you will do is on data structures in one way or another, right? Once you get past assignment 1, most of the questions that you will be asked to write will require you to use data structures in one way or another. The for loop is special syntax which makes it easy to iterate over the elements of a data structure with a much decreased probability of resulting in an infinite loop. You have to work, you can produce an infinite loop with a for loop, it's just a lot harder. So, what is a for loop? I will illustrate on the blackboard. So let's say we had a data structure, right? Let's call it T for tuple. Contains a 1, a 2, a 3, a 4, and a 5. A for loop is structured like this. This is how you write a for loop. For element in tuple. This here is a variable name, and you get to choose the name. You don't have to use E. You could say, capital letter V for variable if you want, You can choose anything to go here, but this has to be the data structure that you are iterating over, right? You then perform some calculations. So this is how it works. On the first iteration of this loop, V has the value of the first element of the data structure, right? It executes the loop, or it executes the body of the loop. When it reaches the end, it passes control back to this beginning part, right? At which point, V becomes the next element in the loop. It iterates through the loop again, right? Returns control, V becomes the next element in the data structure. It continues this until it reaches the end of the data structure, iterates through, checks this, performs the check again. Since there are no more elements in the data structure that you can assign to V, it terminates the loop automatically. All right? So it basically goes like, okay, done the loop, and then control continues on with the rest of the program. This has a few advantages over while loops. Number 1, there is no counter variable. You remember how I said that most infinite loops, in fact, most infinite loops occur because you forget to increment the counter variable, right? Since there is no counter variable to forget, there is no possibility in a for loop of creating an infinite loop by forgetting to do something with the counter variable, by messing up the way that you've written the condition. Any of that type of error is excluded using a for loop construction. Make sense? So, that being said, it is possible to get into an infinite loop using a for loop. What you have to be doing is modifying this data structure itself. If during the execution of the loop body, you, for example, add 2 more elements to the data structure for every time this loop iterates, it's just going to keep, this data structure is going to be growing faster then the loop can process it. Therefore, you will have created an infinite loop. However, so long as you're not modifying t, you're relatively safe with respect to that. Incidentally, that is Mr. Moore's golden rule of for loops in Python. It never modify the data structure that you're iterating over with a for loop inside the body of that loop. Never, for any reason. Declare a new one and modify that, but leave this one alone. All right? It's just like, it's such good practice that it passes beyond good practice into the realm of you should probably just never do it, if that makes sense. In programming, there are many things which are possible which are completely inadvisable. So let's take our linear search algorithm that we just did and revise it with a for loop, just for the purposes of demonstration. Lin search. We'll just take the exact same algorithm. What is going on with my keyboard? Lin search 2. And we'll use a for loop instead. So, first let's set up the central loop. For e in t do something. We don't need I plus equals 1. We don't need I equals 0. We don't need this condition. We do still need this data structure. We still need the if statement inside of it. And the stuff inside that. There. And if we execute that once again, oh, I got an error. Let's see, I is not fine. Oh, yeah. Oh, yeah, okay. I see my problem. E2, E is equal to E2. So I've run into a bit of an issue. Using the while loop, this exposed to the indexes, right? Here, the index is no longer exposed, so I would have to keep a secondary counter variable that would keep track of the indexes. Another way of doing this is if you want to iterate over the indexes rather than the elements of the thing itself, which this is something we're going to see in a bit, we do range, the length of t. What range does is it creates a data structure on the fly with all of the elements up to and not including the number which is specified here. So this creates a data structure, a linear data structure, which just contains all of the indexes that we might want. Therefore, we can say for I in range this, I is equal to, if t at I is equal to e append I. There we go. Again, although this is a lot closer to the while loop than if we were just, for example, returning a Boolean true or false based on whether or not the thing was in there or not. Notice that we still don't have to have the line which initializes I at the top, and we don't have to have the line which increments I at the bottom. This is still a safer way of going about it than a while loop. And this should have the exact same, come on, where are we here? Did I save this? I didn't save it. Okay. There we go. So, you can see this version and this version produce the same results. These are equivalent functions. Make sense? Any questions about that so far? Good. Excellent, in fact. So, as further demonstration, let's say we wanted to print in sequence all of the elements of some string. If we were to do that with a while loop, we would initialize the index, we would have the condition testing against the length of the string, we would have to remember to add 1, and this line here is also equivalent to the assignment statement that's contained within the for loop. So to reproduce the functionality of the for loop, you need a program that contains 6 lines of code, whereas with the for loop, you can accomplish the same thing in 3 lines of code. The fewer lines of code you have, the more likely your program is to run without bugs. This is kind of a truism. The longer your program is, the more opportunity you have to introduce a bug into that program. So keeping your programs short, while not exactly the same thing as keeping them correct, it helps you keep them correct, right? So, not to mention, shorter programs also tend to run more efficiently. So, sometimes the people in the class have competitions to see how few lines of code they can answer the assignment problems in. Which, if you're throwing in things like inline if statements and stuff, you can even do inline looping if you really want to. You can accomplish, I think, pretty much everything on assignment 1 in 1 line if you really want to. But I don't necessarily recommend that if you're a beginner. But if you've programmed before, it's a fun exercise. So, good. So, if we want to do something numeric with I, for example, counting from 0 to 10 and, printing out all of the numbers between 0 and 10, which, is somewhat facile, but there you go. Again, we can use the range function to create an in-place data structure that the for loop can iterate over. The one constraint about for loops is that they absolutely require the thing you're looping over to be a data structure, and not just a data structure, but a data structure that Python considers iterable. Technically what that means is that the class which the data structure is derived from has a definition for iterable, which is a thing that lists and tuples and sets and dictionaries all have defined. So, range. Range actually behaves reasonably. The way that it behaves is a reasonable approximation of the list slicing operations that we performed previously. Basically, the inputs are the same and behave very similarly, but what's produced as an output is a bit different. So, if we have range, I have to do it in Python, geez. All right, range 10. What it's displaying to you here is a quote-unquote range object. In order to actually see the structure of the thing, all you have to do is cast it as a list. So this is the range that is produced by requesting range 10, right? It's very simple to, expand this, whereas that would take a long time if you were to type it manually. The range object produces it very quickly if you know what you want. Similarly to list slicing, you can specify a start point and an end point. So let's say we go from 50 to 1 minus 100. There you go. And you can even, as a third optional argument, specify the amount to count by. So that's how you create data structures on the fly. When you use this in a for loop, this data structure is produced and then immediately consumed by the for loop. Once the for loop terminates, the data structure itself is lost to history. It is what we might consider an anonymous data structure, since it's never assigned a variable name, right? Because it's never assigned a variable name, there's no way of referring to it after the loop is terminated. But, you know, it's reasonably easy to just produce these on the fly. So do you really need access to it afterwards? Who knows? Keeping it anonymous is certainly a great way to prevent you modifying it. So, and again, that's my golden rule of for loops, is do not modify the data structure you're looping over. Make sense? Any questions? Good. So, yes, range object, we've talked about that. So one thing to note about this, the range object produces integers, so if you want a version that produces floating point numbers, for example, you have to code it yourself. Printing a list of even numbers, for example, for x in range from 0 to n, count by 2, with n is 50, print each element of x. This would, you know, essentially do the same thing as I just did, but print them in a vertical list, because every time you call print, implicitly it adds a new line character at the end of what you're printing, so that every time you print something, it's on the next line, with every invocation of print. Incidentally, you can change that if you really want to. Print not new line terminated, end is equal to tab. So even within the command prompt itself, you can like print something on the next line and then have the next line come in at the end of that line by not having the print statement print a new line at the end, which is what actually pops the command prompt to the next line. You can, in this particular example, I just inserted a tab character instead, but you can actually insert nothing if you want to. It doesn't really matter, but anyway, I just thought that might be interesting. So, linear search using for looping, which is, you know, something we already talked about. Factorial iteratively using a for loop. So you guys, I hope, remember the factorial function from last time. We'll be talking about it in a bit. Don't forget it, because we'll be talking about it next week as well when we talk about recursion. Rather than using a while loop, what you can do is you can generate a range from 2 to 1 minus n plus 1, which of course comes out to n. So, why do we start at 2? Anybody? Yes?
1 times anything is not the number?
Yeah, so it's useless. You're just wasting a step if you include 1 there, right? And of course, if we started from 0, we would always get 0 as a result, because anything multiplied by 0 is 0. So, we have our accumulator. For every element in this data structure we're generating, we multiply that to f, and then return f at the end. There is no counter variable to forget to increment. There's the difficulty of constructing the loop condition is replaced by the difficulty of getting the range correct. But here's a little trick. You can always just generate a range and view it by printing it to verify that the range is correct. It's a little bit more difficult to do that with a counter variable, right? You can't like just print it. You'd have to actually get the loop structure correct before you print it, right? Which you know, if it's an infinite loop, you know, you've failed at the first hurdle. Make sense? Good. So let's just, let's review a few common problems, a few common pitfalls that occur when people write loops. So, incorrect initialization, particularly that of accumulators. Think about our factorial problem. If you just threw variables in without really thinking about what you were doing, you might be inclined to initialize f to 0, right? Because you initialize lots of things to 0. It's very common to initialize things to 0. However, in the case of factorial, if you initialize your incrementer, or if you initialize your accumulator to 0, anything multiplied by that is going to also be 0, thus producing an error. Incorrect termination of the loop condition. Misplacing greater than and greater than equals. Getting these confused and swapped around. Very, very common error. What this normally results in is your loop either iterates one more time than it should, often creating what an array out of bounds error, or an indexing error as it's called in Python. Basically, so let's say we had this data structure, right? What happens if you're iterating over this with a while loop and you try to access a value at the end that doesn't exist? That's obviously an error. That's what you would get if, for example, the loop condition you used was I is less than or equal to the length of t, right? The equal to means that this is going to iterate when I is equal to the length. But the length of an object is always one more than its last valid index because of 0 indexing, right? So this would result in an error. This is actually the nicer of the two situations because it will present itself almost immediately. The other one is slightly more pernicious, shall we say. So let's say rather than try to read one more element than you have, you don't quite read enough. You stop at 6 and don't get to 7. Your program would still be erroneous in that if, for example, in a search algorithm, the thing that you were looking for occupied that last slot, right? You wouldn't find it because you stopped searching before you hit it. But in 6 out of 7 cases, that error doesn't even appear. Because in 6 out of 7 cases, the number you're searching for is not the last element. And this ratio gets worse the larger the data structure becomes. So, an error of this type may not even be caught by you until, say, your software is shipped. And then your customer returns a bug report to you if they're a nice customer. And if they're not a nice customer, they just don't buy your product ever again, and tell all their friends never to buy your products ever again as well. Yeah, this type of bug, because it doesn't result in an explicit error every time, can be a lot harder to find, right? So you have to be watching out for it. Other errors which are common. Oh, incidentally, I consider this to be an off by 1 problem because when this is applied to an index, that creates an off by 1. That's what it's called, as an off by 1 error. Infinite loops caused by incorrectly updating the index, which we've talked about several times, and improper bracketing or indentation of nested structures. Cool? So, let's talk about this program. I will give you a minute to examine this program. I would like you to tell me how many errors this program contains. The purpose of this program is to count the number of occurrences of the letter n in a string, which is denoted sequence of characters. Right? Okay. How many people think there is one error in this program? Well, I should say, how many people think there is exactly one error in this program? Because, you know, if you think there are 4, then you also think there's one error, but anyway. 1 error? 2 errors? 3 errors? 4 errors? Don't know how many errors? Would just like to break early for lunch at 10:30 in the morning errors? Okay. So, what errors do you think this program contains? You at the back, sir.
You're calling on x when x is undefined freehand?
Yes. This use of x requires x to already be defined. This is a write operation on x, which requires a read operation on x to be performed first. X has not been assigned to or declared at any point previously in the program, so if you try to execute this line of code, that will result in an error. Thank you. Who has another error for me? You at the back, sir.
I can't be equal to the length of the sequence.
Yes. Yeah, I just talked about it on the board, didn't I? This greater than equals will cause I to exceed the size of the sequence which is input, therefore causing an index error when the loop reaches its terminus. Anybody have any other errors? A lot of you said 3, so yes? I is indented too much. Yes, thank you. So, the way that this program is currently structured, I equals I plus 1 is inside of this if statement rather than the loop itself. If you wanted at the level of the loop, you would have to decrease the level of indentation by 1 tab. So this is, in my opinion, the most interesting error, because this error would only sometimes cause infinite loops, which is kind of interesting. So this would not cause an infinite loop if sequence was composed entirely of the character n, right? Because I is only incremented if the current element in the sequence is equal to n, right? So the first character that's not n that this thing tries to run on enters an infinite loop, because this condition becomes false and none of this is executed, which means you don't increment I. But so essentially this thing, this program as written, only correctly counts the number of n's in a string when that string is only composed of n's. Does that make sense? Good. Very good, class. Very good. So there you go. So, I've already kind of talked about this a lot, but, you know, just in summary, if we are to compare for loops and while loops, for loops automatically initialize and increment the loop variable, thus avoiding certain classes of errors. you know, programmers survived just fine before the invention of the for loop, but, you know, for loops make it somewhat easier. It's one of those little modern conveniences, shall we say. One thing about a for loop, though, you can't add additional conditions to the loop condition, right? You can do that in a while loop because all that you're using at base is a standard Boolean expression to control the loop's execution. In a for loop, you can't do that. You can't just take this, you can't take like this clause, add it to the loop condition. Not possible. This is interesting because, you know, there are definitely things you can do with a while loop that you can't do with a for loop. Like, for example, you could write a program which takes input from the user, says something like, you know, say the letter N, right? And so long as the user hasn't entered the letter N, it re-prompts them for the letter N, something like that, right? Not possible to do with a for loop because there's no data structure underlying that transaction. Definitely possible with a while loop, only because while loops use arbitrary conditions. Basically, at that point, you're relying on the user themselves to eventually be in compliance with the loop's condition. But, you know, so you can't do everything with a for loop, but those things it does very well and better than while loops. Make sense? Good. So, for loops may necessitate jumps out of the body of the loop using return or break. Incidentally, there's a third one called continue, which jumps to the next iteration of a loop, which might also be useful. So, while loops allow a single exit to, and termination condition and make that explicit. So, you know, that's kind of like, you know, you can write both of these in this manner, but, you know, because a for loop, its inclination is to iterate through the entire data structure, regardless as to whether it's found the thing it's looking for or not, right? You know, if you have a data structure that contains 3 million elements, and you find the one that you're looking for after 300, it makes sense to terminate the loop, because otherwise you would be iterating through much like a large amount of material that you don't actually have to iterate through, thus saving lots and lots of time and energy. So you would need a break statement. With a while loop, you can put that test right there in the condition, so you don't require this break statement. Basically, there's a this gets into a very old prejudice. Okay, to explain this whole save return statements for the end thing, I'm going to tell you a tale of the history of programming as a science. Way, way, way back, before the common adoption of higher level programming languages like C. So back in the 1950s and 60s, we didn't have such luxuries as if statements and while loops. The only mechanism that you had for controlling the flow of execution of a program was something called a go-to statement. Go-to statements are conditional branch statements where basically when you hit that instruction, it modifies the program pointer and jumps you to a different part of the program, right? Back in these days, programs were extremely messy. Essentially, if you have a program, right, say you have 3 labels. The labels are the things you jump to, right? and you have like go to C, go to A, go to B, you know, go to C, go to A, and if we imagine we have like some instructions between each of these, right? You know, this guy goes here, that guy goes there, this guy comes here, that goes here, that goes there. You can see that it becomes very messy very, very quickly, right? If you use gotos enough, what you essentially do is break down the linear structure of the program itself in a manner which makes it almost impossible to read. So, the thing that was done to solve this problem, because using goto statements can create programs that are completely unreadable to anybody except the person that wrote it, including sometimes the person who wrote it. Certain goto structures were standardized and turned into if statements and while loops. At base, when you compile if statements and while loops, they are compiled into goto statements at the level of the machine code. That's because the CPU itself doesn't have an instruction for an if statement. It has a goto instruction. All it can do is like directly manipulate the program counter itself. Like, you know, you can imagine like a series of numbers running down the side here, right? And when you're when you go to B, you're actually going to 5, and performs all of those substitutions. That's how it actually works at the level of the CPU, right? So essentially, all of these gotos were, you know, they had their awesome power constrained by if statements and while loops and other associated structures. So what are return statements and break statements? What a break statement basically is it's like a quasi-goto that you can use inside of a loop. Because it's like, you know, while it breaks you out of the loop, what it's essentially doing is it's a jump to whichever label exists at the end of the loop, right? So, a principle of programming which was established back in the 1970s which has, you know, basically been extremely important for programming as a discipline is thou shalt not use gotos ever for any reason whatsoever. Because unless you are programming in assembly language and you don't have if statements that you can use. Because this condition, and you can imagine how much worse this gets if you have a program of any considerable size. This is a condition which is generally referred to by programmers as spaghetti code. Because you look at a piece of code like this, and all you see is a great big ball of spaghetti, where you have lines of execution starting and ending and looping in against each other, and it just, you know, it's like you have a line here and a line there and a line there and a line there, and all, it's just a big mess. Messy code, bad. So use if statements. And that's what they're getting at here is like, try to reduce use of break statements and return statements, because every time you introduce multiple return statements, you're introducing multiple lines of execution, and you run the risk of making your code into a spaghetti ball, right? Now, see, the frustrating thing about spaghetti code is that it can work fine, right? It's just unreadable. So, you know, there's a joke that that programmers sometimes make is if you want to guarantee your job security, make your code completely unreadable so they can never fire you, right? But that's not good practice. Anyway, any questions about any of that? because we're just about done this topic, and I'd like to move on to the next one. Good. Excellent. You guys enjoying the class so far? Yeah? Finding it interesting? It's like cool, right? It's like, you know, programming is a pretty good nerd trap, so if you happen to be a nerd, you know. It's like 3D printing. Has anybody tried 3D printing? Yeah, isn't it cool? But like, there's so many like technical stuff that you have to refine about it that like you can spend hours and hours just like playing with the different values on the printer to get your print to come out a little bit nicer, you know. It's like, man, there are certain things in this world that are just nerd traps, and if you're a nerd, you can get stuck in it for weeks. Anyway, so good. We continue our journey of exploring what it means to code. This topic I consider to be, like in my brain, I separate the different topics in the course by like beginner, intermediate, advanced, basically. This is the last beginner topic. After this, we'll be on to functions and recursion, which I consider to be the first intermediate topic. You know, this is like beginner, intermediate, advanced relative to the course itself, not relative to like programming as a discipline. This is still an introductory course. I just want, you know, you may not feel like this is an introductory course by the time we get to assignment 4, but you know, it is. It actually is. If you want to do like more computer science courses, then, you know, well, you got to get at least a B in this. So anyway, we're going to talk about structured data types. We have talked about them a fair amount already. We have discussed at length tuples and strings. We are going to introduce 3 more and then do some examples. Lists, sets, and dictionaries. So, let's get on with it. So the list. Like tuples, lists are ordered collections of data where elements do not have to have the same type. Elements can also occur multiple times. That is not going to be interesting as a distinction until we talk about sets, which do not support repeated elements. The main difference between lists and tuples is that lists are mutable. They may be updated, whereas tuples are static and cannot be changed after their creation. The syntax for using lists is precisely the same as is used for tuples, except you use square braces instead of round braces. Welcome to computer science class, or as I call it sometimes, attack of the many types of parentheses. There are 3 main types of parentheses that you will need to know and memorize if you want to be an effective computer scientist. Round braces and square braces are both types that you will need. So square braces, you know, we're going to be using those for lists. Please don't confuse this with an indexing operation. It's kind of like different things mean different things depending on context. You know, like if you remember for loops, we use the term in the for loop. It doesn't mean search in that context. It means iterating over everything in this data structure. So, like, you have to be aware of the context of the structure when you're using it. Anyway, so list 1, 3 true potato. The length of the list, of course, is 4. If we print the third element, that will be, of course, potato because it's 0 indexed, right? And most interestingly versus tuples, we support item assignment. So this is a valid operation, whereas on a tuple it would not be. It overwrites the element at index 2 with the Boolean literal false, right? This is a game changer. That alone means that you will probably use lists for most of the things you do rather than using tuples. Tuples are actually not especially common in use in like real world usage. Most of the time you will default to using a list. Lists should be your default aggregate data structure in Python. They're not quite as efficient as tuples in terms of memory usage and runtime, but the flexibility afforded by them sort of pops them over the edge and makes them more useful in a practical sense than tuples. Though you should be aware of both. So, this is how you work with a list. Empty lists are denoted by empty square braces. You create a list by having a comma-separated list of items delimited by the same square braces. You may notice we have the same slicing operations available on lists that we had available on strings, and they operate in exactly the same manner. Concatenation operates in the same manner on lists as it does with strings or tuples. We have the length operation, which works the same. We have the search operation, which works the same. We have the repetition operation, which works the same. And count and index both work the same on lists as they do tuples. You may notice a theme. Pretty much all of the operations supported by tuples are also supported by lists. This means when you write a program for a tuple in Python, the overwhelming majority of the time, that same program will work on lists with 0 modification. However, with lists, we have an extended set of operations which take advantage of the fact that a list is mutable. These are not operations which are applicable to tuples. Number 1, and perhaps most usefully, append. To append means to add to the end of, right? An appendix is a part of a book which has been added to the end of the book. So, why would I do that on the chalkboard? My goodness. So let's pull up our Python thing. List 1, 2, 3, 4, 5. L.append 6. L now has 6 things. Notice that we did not have to reassign the variable, right? If we were working with tuples, we would have to do t is equal to t plus 6, which is a singleton tuple. That's how you write a singleton tuple, by the way. But we don't need the reassignment if it's a list because we are changing it using mutability rather than reassignment. We can extend with another list, which is operationally, it's pretty much the same thing as concatenation. Right? We can insert an element at a particular index. So let's say I want to insert at index 3 the string potato. This is an insert operation, so notice, rather than overwriting element at index 3 with potato, the whole thing gets shifted down and extended, right? This is inserted rather than overwritten. If we decide we don't like that, and we want to remove the element at index 3, oops. That removes the actual element. It's not by index, it's by, yeah, that's an error in the slide. We can remove potato. There we go. And insert at index 2, 3 to reconstruct it. There we go. We can return take an element and remove it from the list by index, and then return that as the return value of the method. So I might say x is equal to l.pop element 4, x is 5, and L has had that element removed. And we also have L.reverse, which does exactly what it says on the box. Any questions? Yes?
What did you say was wrong with this slide?
In this line here, this is not, you don't remove by index. You specify which element you want to remove, and it searches for that element and removes it if it exists. Any other questions? Good. So, the next bit is talking about aliasing, which I'm probably going to do on the board. So, when we are working with these types of data structures, it's interesting to know what L is in the absence of the indexing operation, right? Essentially, what L is, just on its own, is it is a reference to the area of memory where the data is contained, right? So let's imagine we have memory. This is normal notation for memory because it's supposed to look like a hard disk, even though it doesn't look like a hard disk. Let's say we have at address 6000 a sequence of numbers 1, 2, 3, 4, 5, 6. Right? This is our data structure. In another location in memory, let's say memory location 8000, we will have the address of the beginning of the array. The program keeps track of variables by keeping a mapping between these memory cells and the names that you've given variables. So inside of the program, there will be a table, right? variable, and address. So essentially, L will be given address 8000, and that's in our table, right? So functionally, how this works, often when you see these types of things written down, you don't see the number written explicitly. What you see is an arrow to the first cell of the data structure, right? In other languages, such as C or C++, we call these pointers because they point to memory cells. Inside of Python, we call these aliases for no particular reason. So, understanding that L is not the data structure itself, but a reference to the data structure, explains some weird behavior which I'm about to show. So, we already have our list L, right? Let's create a new list M, assign L to it, right? Let's then make some modification to L. Let's say L at 2 is equal to the Beatles, for no particular reason. So L now contains, as its third element, the string the Beatles, and so does M. What a lot of people think goes on here, in this line right here, is a duplication of the data structure, right? We duplicate L, create a copy of it, store it in M. With tuples, you would be correct. But with lists, because lists are mutable, you are not creating a new entire data structure, you are copying the reference. So, what you're doing is you're saying, okay, open up a new memory cell, assign that to M, copy the value here, which is 6000 over here, 6000, that's copied, that's a pointer to the same data structure. So, because M points to the same region of memory that L does, any modifications which are made to L are also made to M. So, thus, we say that L and M alias the same memory. That make sense? Any questions about that? I know this is like getting very like computer architecture-y, but you know, it's it is what it is. So like this can be demonstrated from the command prompt if you expose the true value of L and M. So if you say ID L, and then maybe put that in hexadecimal so that it makes sense. There you go. Memory addresses are typically represented in hexadecimal. You'll see we get this long string of numbers. This represents the actual memory, the actual value that is held at that place in memory. I am using ID, I am referencing this table. If I then do the same thing with M, you will notice that M has the precise and exact same value as L. That address is the beginning address of this data structure where it's actually held in memory. So both of these guys are referencing the same place in memory. Make sense? Good. So, the question becomes, how do you actually break out of this then, right? Because, it may, you will probably be in a situation at some point where the thing that you want to happen is you want to copy a data structure, right? Well, there are some operations which mutate the data structure, and there are some operations which generate a new one. I refer to these as mutating and non-mutating operations. So, something like the assignment here, right? That does not change any data structures. No new data structure is being created. List slicing is a way that you can create a brand new data structure. And if you don't want to actually perform a slice, that's fine, because you can just slice from the beginning to the end with no skipping. So, n is equal to L from the beginning to the end. So, if we modify n, say n at 2 is equal to the Rolling Stones instead of the Beatles, there we go. The modification has been made, and if we view L, L retains its previous value. If we take a look at the ID of, or if we take a look at the actual the memory address represented by n, you'll notice it is not exactly the same as that of L. You'll notice that the characters are the same up to, this one, which means that these are both being held in roughly the same region of memory relative to the entire computer system. But they are different, which means they point to different data structures, which means any modifications to n occur at this address, any modifications to L occur at this address. So they're separated. Does that make sense? It's a tricky concept, but hopefully we're not. Hopefully that came through reasonably. Incidentally, if you want to know, and this is kind of interesting, if you want to know what an indexing operation actually is underneath the hood, if you take a look at this, let's just knock this down to like numbers which are more reasonable. So the way that memory is stored here, right? This is like not quite true with respect to the numbering, but it works. It's actually incremented by 4 because you would be going along byte boundaries, but let's just work with it like this for now. These are the memory addresses of all of the elements of the data structure, right? 60, 61, 62, 63, 64, 65. When you say L at 3, what that's actually being interpreted as is the ID of L plus 3, right? Since the ID, the value at L, not the ID of L, but, let's just say L, L plus 3, the address of L. Anyway. In C, you have actual explicit operators for this, but, let's just say, address for now, right? So, we take a look at L, right? L is actually having the value of 60 in this case. We add 3 to it, and follow that to the address indicated by that number. So that will be this guy right here, right? And that is why everything is 0 indexed, right? That's why L at 0 is the first element, because it is the element with 0 offset. Because the way that it's stored in the computer is without any kind of like header bit, right? Because that would waste memory. You can imagine like if each of these guys had like a bit at the front that was unused just because we wanted to number from 1 instead of 0, how much memory would be wasted by that, right? It would add up over time. So 0 means with 0 offset with respect to the actual addressing in memory. That's why indexing occurs from 0. Make sense? Cool. So, this is all basically just the stuff I've said. This is a question. The answer to this question is actually already given in the slide, but anyway. So if A is 1, 2, 3, A points to 1, 2, 3. If B is equal to A, both A and B point to 1, 2, 3. If C is 4, 5, B, we are including the reference inside of another data structure. So C is 4, 5, and then a pointer to 1, 2, 3. This would print, by the way, 4, 5, 1, 2, 3, and then like a list within a list. If we assign A at 0 to C at 1, C at 1 is 5, A at 0 is 5, is set to 5, it was formerly 1, and E, if we set E to D at 0, I missed one. D is C at 2. C at 2 is a pointer to this data structure, so D also becomes a pointer to this data structure. E is D at 0. D at 0 is 5, therefore the result of this calculation is 5. I know I went through that quickly, but you know, it's I would never ask you this on a test. Let's put it that way. So before we move on, practical applications of this stuff, right? Because you might be like, okay, so I just memorize a couple of rules, I use the slicing operator to copy, and I just forget about the rest of it. Why would this impact the way in which things run? All right? When you input lists into functions, the way that the local naming of that list occurs in a function is using standard assignment, because Python uses pass by assignment as its way of passing things into functions. So if you have, say, def func with a K, Funky Town, L, there we go, and then you're doing stuff, and you use func on some pre-declared list L2, or let's call it M, where M is 1, 2, 3, right? The way that it works in Python implicitly is you have a line here that doesn't really exist, that you never actually write but is still there, where L is equal to M, where M is the M that was passed in, right? So this step is assignment in the same way that assignment works everywhere else. Which means when you pass a list into a function, modifications to that list which are made inside of the function appear outside of the function. Right? So what that essentially means is when you pass a list into a function, that list is also implicitly output of that function as well as being input. Any modifications that you make to it will appear after the function has terminated because of aliasing, right? So that's something you should be aware of. In the same way that it's bad practice to modify the data structure that you're iterating over while you're in a for loop, in most circumstances, I would consider it bad practice to modify the data structure that's being given as input to a function inside of that function for the same reasons, right? If you need modifications to it, it's much safer to copy it to a new data structure and work on that one, leave the input alone, right? Now, Python, because Python is Python and Python is the worst, has absolutely no problem with you making assignments to the variables that you receive as input, right? But in general, I would consider it bad practice. In some languages, you can actually declare, you can like write constant L. You'd also have to do a, you'd have to give it a type, but that essentially makes it read-only in some languages, like C, C++, which it restricts the user from being able to modify it, which may be very useful. Because, you know, users are the worst. They just are terrible. People are much less reliable than machines, as it turns out. Anyway, so slicing. We've already talked about slicing. We've already talked about slicing at some length. Does anybody want me to go through slicing again, or can we skip it? We good? Okay. Good. This is like slicing rapid fire round, which, you know, I'm conscious of the time. So, tuples are like lists, but immutable. Tuples do not alias, they do not use aliasing, and they are faster. They're faster because there's less memory copying. But yeah. So here's the thing about a tuple, right? Because tuples are statically defined, they can never exceed the size that they are upon creation, right? So this kind of gets into other memory concerns. So let's think about memory as being a series of blocks, right? Like a big table, because it essentially is a big table, right? Let's say that you have, let's say you have a tuple that needs three memory cells, right? Let's say this is used, and this is used, right? There you go. And then the rest of it is free. With a tuple that contains only 3 elements, you use these memory cells and you call it a day. You don't have to worry about it any further, because if you make modification to it, what you're actually doing is using different memory and then reassigning the pointer to the new memory, right? So this is just static. It sits there. It doesn't do anything. Good. If it just sits there and doesn't do anything, we don't need any operation to perform over it, right? How about if this were a list instead, right? And let's say we liked appending things to the list, because that's a thing that you fairly commonly do. So we append one item to the list. Boom. We append one more item to the list. Boom. And let's say that the user requests that you append one more item to the list. Where does it append it? It can't. So what does it have to do? It has to copy this memory to new memory that has enough space at the end to be able to accommodate the new list. So, there we go. It it says, okay, copy, 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 add. Right? It doesn't happen every time, but when it does do that, it has to copy the entire data structure, which of course takes way more time than not having to move it at all. So that's why lists are more expensive than tuples. Now, the object of programming languages, basically since the late 80s, has been to try to abstract away all of these memory considerations so that you don't have to know this to program effectively. Like, you can write a correct program without knowing this information, right? But you can't write an efficient program without knowing this type of information, right? So if your goal is just to program, just to get, just to write the program and call it a day, you don't need to know this. But if your goal is to write efficient code that will be run efficiently by servers, etc., this is the type of optimization that actually matters, right? Does anybody know what the most expensive thing about running a big server, like the big servers that like Google or Facebook run? Do you know what the most expensive part about that is? Like in terms of the actual expenses of operating the facility?
Power usage?
Sure, but can you be more specific? It's not the power to run the servers itself. It's air conditioning them so they don't melt. Like, actually, though, a big problem with servers, on the scale that Google uses them, is heat dissipation, right? The thing about a computer, every single operation that you perform dissipates a small amount of electrical energy. That electrical energy, of course, after it's accomplished the work that it has to perform, is largely made into heat energy. That heat energy has to be dissipated somehow, and if you're one of those people that really likes to overbuild your PC, you do things like liquid cooling of your CPU and stuff like that. But most of the time, air cooling is perfectly sufficient. So every extraneous and redundant operation that you perform costs you a little bit of energy and a little bit of heat that's produced, right? It doesn't really, like for something like my laptop, it doesn't matter because it's in a large enough room that the heat dissipation isn't really a factor. But has anybody walked by SharpNet in ABB? You guys know that there's a supercomputer on campus? Yeah, there's a supercomputer on campus called SharpNet. It's one node, actually, of a distributed supercomputer. A few of the other universities in the province also have nodes of SharpNet. But anyway, you should walk by sometime because it's kind of cool. They've got like this big open window in ABB. And you'll notice that in that room, you can see the ventilation in it. And the fact that they've had to really pay particular attention to the manner in which they cool those servers down, right? Like this is actually one of the physical restrictions that you have on servers. So, basically, the more efficient your program is, assuming that that program is being run by a sufficiently large computer, the less heat your program will create, the less heat has to be dissipated by an air conditioning system, the more money your company doesn't have to spend on heat dissipation. So there's actually a direct financial benefit of writing efficient programs. So there you go. Not to mention it's better for the environment. Save the planet. Write less code. There you Anyway, so let's talk about sets. Does anybody need this stuff? Good? Good? Oh, it's recorded anyway, I suppose. Wow, I guess I could now claim that lists are like the SUVs of the programming world, in that most people don't need them for most purposes, but they drive them anyway. And it's killing the planet! There you go. Anyway. Lists are gas guzzlers. There you go. So, anyway. And it's really just for your own convenience. And isn't that really like what the whole car debate is anyways? It's like you can burn oil for your convenience, or you could not burn oil and be less convenient, but it saves the planet. Lists are the same thing. Anyway. So, sets then. How many of you have, at any point, studied set theory? Like, probably the last time you would have seen it is in high school math, or some kind of math course. Set theory. Anybody? One person, two people, a couple of people? Okay, a little bit. All right, so sets as expressed in Python are essentially equivalent. Like the design, the thing that they're trying to accomplish with sets in Python is to replicate sets in the set theoretic sense. So, you know, so what is a set? A set is a collection of objects, right? Or a collection of things. If you have a bag, and you fill that bag with different colored jelly beans, that is a set of jelly beans. If you have a set of numbers, such as the integers, that is also a set, right? You can define this set by saying, you know, you take 0, you add 1, and each number that you get from that by repeatedly adding 1, that is part of the set, and each number that you get by repeatedly subtracting 1 from 0 is also part of the set, thus the integers. You can say the natural numbers are just half of that, you know. These are all sets, right? Some sets can be subsets of other sets. The integers are a subset of the real numbers. The natural numbers are a subset of the integers, right? So we have this kind of abstract conception of a collection of things, right? Now, sets in their most pure form do not have a lot of the properties people think of when they think of things like the integers, right? A set of objects, just as a set of objects, does not have an implicit ordering, right? There's no ordering, like, the way that they define it in set theory is you have what's called an ordering relation, which is, it's kind of like a function. You can pop two elements of the set into this ordering relation, and it will tell you whether one's greater than the other or the reverse, or if they're equal, right? Sets in their most pure form do not have this, right? If you think jelly beans, right? It doesn't really make a whole lot of sense to say, is a red jelly bean greater than a green jelly bean, right? You could, like, say, well, the red jelly bean has a mass of, like, 0.35 grams, whereas the green jelly bean has a mass of 0.38 grams, so you could order them according to size. But this is introducing more information than is actually contained by the idea of you just have a set of different colored jelly beans, right? You would have to know more about the physical objects, and This is a mathematical abstraction that we're trying for here. You could just as easily have a set of colors sort of abstracted from the idea of physically existing jelly beans, right? If you have the color green versus the color red, it doesn't make sense to order them, right? So, sets in their purest form do not have an ordering relation defined for them. In the same way, basically sets start with 0 operations of that type. And if you want operations of that type, you define them for a particular set, right? But, you know, if you have a set of colors, you know, that has the implicit ability to tell if one of the colors is the same as itself or not, right? You can say, is red equal to red in terms of colors? Sets in their purest form might lack that type of comparison as well. But this is getting very abstract and theoretical. So, when we're talking about sets in Python, we're talking about data structures which contain things, but those things are unordered. So a thing that you can't do with a set in Python is use linear indexing to access particular elements of it. You can't just index things. Essentially, like, underneath the hood, all of this is being stored in C arrays, basically, so you don't, like, in the end, this will be stored linearly in the computer's memory, but it's a, Python disallows operations which would imply an ordering between the elements of a set, like, relative to each other's placement. Once you extract elements from the set, then you get all of the regular operations that you have with those elements. But as elements of a set itself, there's no this one came before that one, if that makes sense. So, in mathematics, sets are not only unordered collections of objects, but they are unordered collections of objects without repetition. So, for example, the set of all even numbers less than 10 is 0, 2, 4, 6, 8, or an equivalent set would be 4, 2, 6, 6, 8, 8, 0, 4. The repetition does not matter. The repetition is not kept. And the ordering doesn't matter as well. In terms of set theory, this set here and this set here are the same set. Make sense? A little bit? Hopefully a little bit. So, in addition, there are certain operations on sets which we have available to us in Python. And this is when I pull out the Venn diagrams. So, let's imagine we have a set A and we have a set B. This is going to rely on the idea that you can tell if two elements of a set are the same element. Some of the elements in B and A are the same. So we say that there is a non-zero intersection of these two sets, right? I'm going to start with intersection. A intersect B is all of those elements occurring in both the set A and B. So this is the intersection, right? The way that that is been written in mathematical notation is A intersect B. This is like upside down U with no tick mark. Oh, I'm going to run out of room quickly, aren't I? I'm going to squish them. All right. So, if we have our sets A and B again, incidentally, they don't have to be circles. Union is all of those sets in A and all of those sets in B. Because there's no repetition of elements, we essentially, like anything that's represented twice, if you just like take all of the elements and just like run them in a line together, any repetition will of course be expunged because sets do not support repetition. So you get everything in A, everything in B, just like this. In mathematical notation, this is written A union B. There is a correspondence between this and Boolean and OR operations, right? This would be Boolean and, because it's only those elements which are in A and B. This is Boolean OR, because it's those elements which are in A or B, right? And if you want mathematical notation for these for the Boolean operation equivalents, it's that they actually look very similar to the set notation as well. A and B, A or B. Basically, you turn the round into a point, and you've got the Boolean operation equivalent if you're dealing in mathematical notation. Right? There's just a little bit of formal logic for you. In addition, we have two operations, difference and cardinality. The difference of two sets, if we have sets A and B, is all of those elements which are in A but not in B, like so. This is A minus B. We just use minus. Sometimes there's like a special set minus, like in math notation, they sometimes use like a slash here for set minus, but in Python it's negative, so sure. And then cardinality is essentially the same thing as length, right? It's just the number of elements in the set. Make sense? Any questions? Good. So let's get to syntax. To declare an empty set, you use the keyword set, which is also the conversion function. So you can take a list and convert it to a set using set as a function name. If you provide no argument, then that designates an empty set. Sets are delimited by curly braces. Dictionaries, incidentally, are also denoted by curly braces. Empty dictionaries are used much more frequently than empty sets, so that's why this is written like this and not just empty curly braces, because that's already being used by dictionaries. These slides have an interesting habit of introducing data structures in like the reverse order of their usefulness. But anyway, union is written bar. Intersection is written ampersand. The reason for those notations is in most languages, Boolean OR is written 2 vertical bar characters. So X or Y is written like that, right? And you notice that intersection is like, this one. That's why it's like A or B in Python. Intersection is A and ampersand b, which is a little bit more obvious why. It's like you can kind of, if you need like a mnemonic, then it's like left or right, you know, divide them, this one or that one. Although it in effect does not divide anything but whooshes them all together, but you know, whatever. Set difference is just mapped to the subtraction operator. Length serves as cardinality, and we do still have search operations over sets, although in set theoretic terms we would call this set membership, or you know, X is an element of the set S. So the way that you write this is X element set. Or maybe I think it's without the tick here. Yeah, I think it's without the tick there. Anyway, that's how you write it in terms of set theory. Good. So sets are mutating, or sets are mutable data structures in the same way that lists are mutable data structures. So all of those rules that we talked about with respect to aliasing are also applicable to sets. We have add operation, an IAD operation, a remove operation, and a pop operation. So if we want to add something to a set, we add with .add. If we wish to discard something, we say discard some element. And if we want to return and remove an arbitrary element, we use pop. So arbitrary in this case means deterministic but not predictable. So like there's a distinction between arbitrary but deterministic and random. You can kind of think of it as being random, but it's not truly random. Nothing in a computer is actually truly random because computers are incapable of generating random numbers. The best they can do is what they call pseudo-random numbers, where they take some input number, perform enough mathematical operations to mix it up sufficiently that the resulting number is effectively random, but it's not true randomness because you can't just generate a random number from nothing. It must come from what they call a seed value, right? So, you know, when you're playing a video game and, you know, you're experiencing the RNG of that video game, know that if you modify your system clock, you can probably like get a better outcome on the RNG. Because most of the time, the seed that's used for random number generation is something that like changes quickly anyway, something like the system clock in like milliseconds, right? Do you have a question? No? Okay. Any questions so far? Okay. So arbitrary but deterministic means that the algorithm which is used to determine which elements should be removed is not evident to the user, but the results are repeatable, right? So it's like, to you, it's essentially random because the computer is just picking one, but every time you run the same scenario, it will pick the same one. That's what it means to say it returns and removes an arbitrary element. Any questions? It doesn't come up much. I'll just say it doesn't come up much. So, if we wish to write an algorithm to extract the unique elements of a collection of data, unique elements 1, let's say, we declare an empty set for E in L, for every element in L, S is equal to S union, that element placed in a set all on its own. And then at the end, we return the length of that set. All right? Turns out that you can actually do this in one line, which I will do now. Very easy. let's see, we got L, sure. It's just the length of the set conversion of L. There you go, that's the number of unique elements. I suppose that doesn't really show up because everything in L is unique, so let's give it something that isn't. There. The number of unique elements is 3. Basically, what this algorithm is doing is it's using these set operations to reconstruct the set conversion algorithm that's implicit in set anyway. Make sense? Good. So I think we'll just skip that. So here's our summary so far. We have talked about tuples, lists, and sets. They use round, square, and curly braces, respectively. Lists and tuples permit duplicates, sets do not. Ordering matters in tuples and lists. Ordering is not only does not matter, but is not even a supported operation in sets. Tuples are immutable, but lists and sets are mutable. Any questions? Good. So, let's move right along to dictionaries. Is the pace okay for the lectures? Is everybody able to keep up reasonably well? Give me a thumbs up. Okay, good. So, we move on to the dictionary. A dictionary is best thought of as a mapping between two sets. So, if you have a set A and you have a set B, right? Let's say you have elements inside of A and you have elements inside of B, right? A dictionary, or a mapping, is some relation between these two sets whereby you can access some elements of B from some elements of A. So you can, let's say you had, let's number these, 1, 2, 3, 4, 5, 6, 7. A, B, C, D, E, F. This mapping, this relation, in this case, is defined by 2 yielding A, 4 yielding C, 3 yielding D, and 5 yielding E. Right? The mapping itself makes no assumptions about what these elements are. Right? And similarly to sets, we do not have any implicit ordering over these elements unless you were to, say, extract them from this set, put them into another data structure and, sort them or do whatever it is that we want with them, right? It turns out that these guys are actually quite useful. It's a way of relating, for example, strings to numbers, right? In the example given in the slide, we define a dictionary, read mapping or relation, between month abbreviations and the number of days in that month. So, January maps to 31, February to 38, March to 31, April to 30th, etc., etc. we may access the elements of set B using a known element of set A. So in this case, days in month with January provided as a key accesses the value 31. So this will print 31. Does that make sense? Good. The terminology used, keys, values. So in this case, the keys are 2, 4, 3, and 5, and in this case the values are A, C, D, and E. Of course, if I wanted to make these like valid in Python, I would put little quote marks on there to denote these as strings, right? Because it's like whatever these are, both the keys and the values have to be valid Python, things which are valid Python objects, right? And they can actually be objects in the general sense if they're a value. Like you can map to objects. But anyway, we haven't talked about objects yet. We will though, don't worry. Good. Yeah. So operations. Empty curly braces denotes an empty dictionary because dictionaries are about 1,000 times more useful than sets. So they are given syntactic privilege over sets. The way that you write a dictionary or a mapping in Python, a series of pairs of objects separated by a colon. These pairs themselves are separated by commas, and the whole thing is enclosed with curly braces. So what we say, the way that we would pronounce this, E maps to F, G maps to H. If you want to look up some key E in the dictionary, so the thing you're looking it up by is the first of these pairs, right? These guys are unidirectional, right? It is, it's possible to go the other way, but it's more work. The way that it's designed to work is you access this guy using that guy. You don't access this guy using this guy, right? There's like a big implicit arrow right there. You go one direction. You know? Again, it's possible to write an algorithm that will get you the key from the value, but it's more work. So, you look up a key E using the same square brace notation that you use for indexing. You delete, you still have access to our much vaunted search operation in. In, by default, searches the keys. However, it's actually reasonably easy to extract a tuple of the values contained in the dictionary. So, if you want to check to see if something is in the values rather than in the keys, you just search E in D.values, not just D. I kind of find it like a bit self-documenting to, say explicitly D.keys or D.values in these types of operations, just because it's like, it makes it clear that that's what you're doing, But you don't have to use this one because it's by default here. Make sense? Good. So, length appears once again before our eyes, and if we wish to delete an entry from a dictionary, del, and then you specify which one. Any questions? Good. So let's demonstrate some of this. dictionary. We map 3 to 7. We map apple to orange. And we map true to 5.6. Oh, I need to enclose in, make it an actual string. There we go. So D at 3 is 7. D at apple is orange. And D at true is 5.6. Notice that I'm mixing up all of the data types here, you know? Each one of these keys can be any general object, except for, I think, mutable. It has to be an immutable data type, actually. Now that I think about it, I think if I tried to put a list in there, it would crap out on me. Let me try. 1, 2, 3, maps to, oops. Yeah, unhashable type. Yeah, so you can't use mutable data types as keys, but you sure shootin' can use them as values. There you go. So I'll just explain what it means here by hashable, right? So when you hash a value, what you're essentially doing is you're taking that value, calculating some number from it, which, shall we say, when you hash a value, you get the same hash number out of it each time you hash it. Otherwise, you're just generating random numbers, pseudo-random numbers. So 3 will be converted to some other number reliably each time. Orange will be converted to some other number reliably each time. This saves us the trouble of, like, you know, having to store the actual string whoops in memory, right? Because that could potentially become very large. Some of these, some data types you can't hash, like mutable data types, so you know you can't use those for keys, but you can use them for values. So yeah, anytime you like call, you know, D at apple to get orange, what it's actually doing is it's calculating the hash number of apple, using that hash number to look it up in a dictionary that maps hash numbers to elements of the set of values rather than like directly the actual keys that you're using. But that's kind of like, you don't need to know that. That was just if you're interested in it. Incidentally, though, now that you know what hashing is, you should also know what hashtags are. So, good. Yeah. So, yeah, anyway. D dot values is just dictionary values. D dot keys is just dictionary keys. There you go. Good. So, dictionaries are mutable. You can modify the elements of a dictionary using regular assignment in the same way that you can with lists. Basically, you can almost think of these things as lists where like numeric indexing doesn't work unless you put in all of the numbers, and you can use anything to index it. But yeah, so they're mutable, so this is a valid operation. And the way that you add something to a dictionary that already exists is you simply assign something to the new key. You don't have to perform a special operation. This line here extends this data structure with this additional key value pair. Make sense? Good. Example. Histograms are used to determine the absolute frequency of the items in a collection. The following algorithm can be used to bucket elements into a something that could be easily, graphed as a histogram. So let's assume we're working on strings here. We initialize an empty dictionary for each character in S. If the character is not in the dictionary, we assign to that character and we give it a value 1. That sort of says, okay, this thing is now being tracked. We started off with 1 because we found one of them. If it does exist in the dictionary already, then we increment the corresponding value. The value corresponding to that character when the character is used as a key. At the end, we return D, right? So, if we were to run this algorithm on doorbell, we would end up with D maps to 1, O maps to 2, R maps to 1, B maps to 1, E maps to 1, L maps to 2. Make sense? So, looping over dictionaries. In the same way that the in operation defaults to searching the keys of a dictionary, when looping over a dictionary using a for loop, the thing that is assigned to the loop variable is the key, all of the keys of the dictionary in sequence. So what a for loop does on a dictionary is it iterates through every key in the dictionary in sequence. Oh, incidentally, one thing which is true about dictionaries, which has been implicit in the slide so far, keys may not be repeated. So you can imagine, right, if you had another 5 in here, right, and you were mapping that to F, right, so you added like 5F. If the poor computer had to actually execute that, right, which 5 does it use? It's ambiguous. The one thing that we cannot stand in our computer programs is ambiguity. So you're disallowed from doing that by the fact that anytime you try to reference a new 5, you'll actually just be referencing the original one. So that's kind of implicit in dictionaries, that you can't do that. Make sense? Good. So, the difference comes in, for K in enrollment, if we print K, we get each of the keys in enrollment. 1, 2, 3. If we print enrollment at K, then we print out the values, right? But K itself is the keys. That's how for loops work on dictionaries. Any questions so far? So, let's finish this slide off, and then we'll break for today. All right, because the next section is long and arduous and cannot be accomplished in 5 minutes. So, this is a class participation slide, so if everybody could get your hands ready to be raised. Which data type would you feel is appropriate for the following situations? Tuples, A tuple, B string, C set, D list, E dictionary. The top 5 nominees for best animated film. How many people would use a tuple? Incidentally, you can answer more than once. for all of these, because in many cases more than one data structure is valid, right? So how many people think a tuple? How many people think a string? How many people think a set? Yeah. How many people think a list? Yeah. How many people think a dictionary? So for a dictionary, what are you mapping from?
From the
Nominee
film
and
to the
film, put film as values.
Oh, yeah, okay. You could do that way. So, like film to director, something like that?
yeah.
Yeah. That's kind of extending the definition of what's asked for here, though, right? It's just asking for, like, the top 5 nominations, right?
Oh.
Question?
You could do position and name.
Position and name? Well, if you were just taking nominees, right, you wouldn't necessarily be implying an ordering of them, right? Because if they're the nominees, we're not, like, think about the Oscars. We haven't yet had the envelope opened and see who the winner is yet. So I would say in this case, tuple, list, or set, probably. Shopping list for pizza ingredients and amounts. Call it out. What kind of data structure should we be using?
Dictionary.
Dictionary, yes, because we are relating one thing to another. The names of your cats. What do you think? Tuples, sure. List, yeah. Depending on whether your cats are mutable. If you don't want to give priority to one of your cats over the others, then you might use a set. But we all know that you would have a favorite cat. The courses you took, the year you took them in, and the grade you got. Dictionary, yes, because you are relating a course that you took, well, you could say courses and then a list of the courses you took. You could say the year, and you could take, well, you could also, this one's complicated because you could kind of make it like a nested structure, You would say something like courses, and that points to like a list of tuples where each one is a course, and you would have like a course code, 1MD, MD3, comma, and then a dictionary that would go, or a list, I suppose, year is, you could even do like name here. Yeah, let's do that. Name, 1MD3, comma, year, 2022, and then grade greater than a B. Something like that, right? So, and then you could have like, similar things going on here. So, this example is reasonably important. Up to now, we have not been discussing nested data structures very much or at all. Nesting of data structures is a really, really important concept to get, Like, the fact that a dictionary could have a value which points to a list that contains other dictionaries which have certain values, this is like, fairly important, You could access it like courses, like D is equal to courses, D at courses at 7 at grade, And that's how you would navigate a structure like that, right? Does that make sense? Any questions? No? Okay, I guess we will continue on with this discussion next week. We will talk about how to solve problems. And yeah, thank you very much. See you guys later.